Let's talk about bisection, how it works. It's a very simple idea. Maybe also you have this idea, and maybe also you practiced this idea. Okay, what's the idea of bisection? We have a function and we are looking for the roots of that function. And what do we have? We have an interval. The user provided that interval, and it's of the kind that at the left point the function value is positive, and on the right hand side of the interval the function value is negative, or it's the other way round. And if the function is continuous in this interval, there must be a root, and we can find it by the following idea. Take the midpoint. This is a plus b half. Evaluate the function at that midpoint, and then we can exchange either a or b, and thus we get an interval which is only half the length the interval has been before. Depending on the sign of this value. So let's illustrate that. We have f of a and we have f of b. And let's assume the sign of the function value here is plus and the sign of the function value here is minus. Then we evaluate at the midpoint, and let's assume the function value at the midpoint is also positive. And now we can take this interval, we throw away this a and replace a by a plus b halved, and then we have a new interval, and in this interval there is 100% a root, and the length of this interval is only the half of the one before. Okay, what's about if the function value at the midpoint is negative? Then we throw away b and we work with that interval. And if it's that case, minus plus, and we get a plus here, then we throw away this one. And if the initial status was that and this is negative, then we work with that interval. Okay, this is a very simple idea and it works perfect. Let's have an example. Let's use the function logarithm, the natural logarithm of x minus x divided by 3. The natural logarithm, normally we have to write ln of x. In MATLAB they work with log, log, and now we need an initial interval. That's not an easy task for the user to provide such an interval. Let's say the user said, okay, AB, we are looking on the interval 0.53. This interval is of the following kind. Here A is 0.5, B is 3. The natural logarithm of 0.5 is a negative number. Logarithm looks like that. Here is 1, here is 0. And here we have a negative value. Minus 0.5 divided by 3 is also negative, so we get a negative number here for f of a. If we take the 3, the natural logarithm of 3 is a little more than 1, because the natural logarithm of e, 2.7, is 1, and it's a monotonic increasing function. So a little more than 1 minus 1, this is positive, so we are in the situation we need. Then midpoint, a plus b halved, in this case 3.5 divided by 2, this is 1.75. Then evaluate at that point, and if you use your electronic calculator, then you find out this is a negative number. The value of the negative number does not matter if you use bisection, only we have to know it's positive or negative. Okay, then we have the following situation: negative, negative, so we throw away 0.5 and use 1.75 instead, and b is 3. And then calculate the midpoint, a plus b halved. 4.75 divided by 2 is 2.375. Then evaluate at that position. Here we have a negative, this one, and here we have this positive. And if you evaluate here, then you get plus. And so we get rid of this b, and we work with this number replacing 3. We are here. 2.375, 1.75. What is the midpoint? In this case, add these two numbers, divide by 2, and you get a little more than 4 divided by 2 is a little more than 2. And then evaluate. Here we have negative, positive. Evaluate this function at 2.0625. You will get a positive value, and then we know we work with that interval and iterate that process. Okay, this is a very simple idea. Now let's check my script. Okay, so by section we have a continuous real function which is defined on the whole interval a, b, and here we have, for example, that function. And then we are looking for zeros for roots of these functions. The user has to provide a, b such that this is true. This is a formulation for either f of a is positive and f of b is negative, or the other way around. In this case, the product is less than 0, and if they are of the same sign, then the product is positive. So this is a formulation for different sign. And then let's take the midpoint, evaluate at the midpoint, and then what can happen? The function value can be 0. Okay, we did not talk about that so far, but what is if this function value is 0? Okay, this is what we are looking for, so this would be a very lucky case. If the function value is 0, we found the root, but in numerical examples this will almost never happen. Then let's check the sign of the function value at midpoint and compare with f of a and f of b, and then replace and iterate that process. Okay, this is a visualization. Function value here positive, function value here negative. Take the midpoint, evaluate at the midpoint, same sign as here, so throw away this part. Then we have only this interval. Take the midpoint, evaluate at the midpoint, compare the signs. It's the same sign as on the left hand side, so throw away this part. And then we work with that. Take the midpoint, evaluate, compare the signs. Okay, throw away this part, and so on. What is an advantage of this idea? It's very easy to understand and so very easy to implement also. But the user has to provide a and b so that we have different signs of the function values. This is a disadvantage because the user maybe has absolutely no idea about the structure of this function. So it might be of that case, and he's looking for the roots, and he does not know that the roots are here. And maybe he says, okay, let's use that a, let's use that b, but this is not a choice which is allowed. So this is really a disadvantage if you want to use bisection. One more disadvantage, you can find only one single root, not two roots. If you have the following situation, then if this is your b and this is your a, you take the midpoint, you will throw away this one, throw away that one, and then you will find this root, but not this root and not this root. this is a disadvantage. And also let's see how do the other ideas compete in that point. Okay, and then convergence speed is only linear. The length of the interval is only halved in every step. That's not so clear if this is an only, because halving is not so bad. So this is the implementation. The user provides a function we can evaluate. The user provides an A and B, and he tells you how long should the process be iterated. Let's evaluate at xa and xb. Let's check if they are of different sign. If not, we return an error. And so here we do the following. We always want to have positive at A and negative at B, and we do that by swapping A and B. It doesn't matter for the code following. So as long as the distance from A to B is more than the tolerance, take the midpoint, evaluate at the midpoint, then check. If the function value at the midpoint is more than 0, then we replace A, and that's what we do here. And if the function value is negative, then we replace B. Here in the code, missing is the 0, the check for the 0. Now let's keep the code simple. If it is 0, the code also will decrease the length of the interval, so it works also in that case. And if the tolerance, the distance is less than the tolerance, then we can finish. And what will we return? We could return an interval AB. For the user who knows what's going on in bisection, he will maybe prefer returning the interval, but the normal user says, okay, what is the approximation of the root? And then we can return the midpoint of our interval, and this is a good approximation of the root we are looking for. Okay, what will we do now? We will run that code, we will work with that code. I inserted some extra lines, this one steps, and then I print this number of steps we did so far, and I print the interval we are working with in the moment. So let's call that function, and let's illustrate with our function from the last video with the rope around the Earth. There we had an R. This is the radius of the Earth. It's 40,000 kilometers divided by 2 times pi. Then you get the radius in the unit kilometers. If we want to work with meters, then we do that. And then we find out it's 6 million meters, the radius. And then we have the function. This is the syntax for a function, and the function was r squared, the r from above, plus r times x plus a half squared, and minus r divided by cosine of x. And we are looking for the roots of that function. So we can call roots and the initial interval was 0 and 1.5, and we can iterate that, let's say, to the tolerance 1 divided by 10 to the power of 6, 1e minus 6, and then let's run. Yes, I forgot to square that. This is the function we are interested in. Okay, and now let's look for the roots in this interval. Steps should be increased by 1. And now let's run that function, and we see the following. We start with the interval 0.15, then the midpoint is 0.75. We evaluate at that point, and it turns out that the value of the function is of the same sign as at the position 1.5. So we exchange 1.5 by 0.75. Then we take the midpoint, this is 0.3750, evaluate the function, we find out it's of the same sign, the function value, as it is at this position, so we exchange again 0.75, the right hand side, and so we do a lot of times. We always exchange the right hand side, but not infinite long. And here, when we have this interval and we take the midpoint, this is this value, and then it turns out this function value is of the same sign as it is at position 0, and so we exchange the 0 by the new midpoint. This is the same number as it is here, and it's 1.1719 times 10 to the power of minus 2. So this goes on and on and on. Then we finish with that interval, and the user gets the information. This is the root of this function, or better, this is an approximation of the root of that function. Then in the last video we learned that there is an alternative, and the alternative to the formula above is tangent of x minus 1 divided by 2 times r. And if we work with that function and then we call root bisection, if you compare, you will see that there's absolutely no difference. Every step is the same. Why is that true? Because the root is the same, and so the process will work exactly as it did before. And so also after 21 steps we get this interval, and the algorithm will return that approximation of the root. So okay, this was the very simple idea of bisection and how does it work.